we're given this field and a sphere here with the radius of 2, and we're trying to compute the flux. And we're looking at this complicated equation, and well, let's say we had a balloon here, and we were filling the balloon with air, and we measured how fast that was expanding, and maybe you knew how long that outer surface was. Would you probably be able to calculate how much air was going into the balloon, causing it to expand? And the answer is yes. And that is what the divergence theorem is trying to get us to do. So if we're trying to calculate, basically that S is a surface integral. So the integral across the surface, which you'd usually need to have a double integral for that kind of a thing to integrate across the surface. But let's say you were trying to do a double integral across F, and you had this this normalized normal, and then this dotted thing. You could try to calculate all of that by hand, or you could take a quick shortcut. We're not even going to go into what all that stuff means because it's not really going to help right now. But we will take a look at the next part, which is what this is trying to say. So if you can figure out how fast it's expanding there on those edges, the speed of the expansion, then you'll be able to calculate how much air is going into it. And this side tells you how much air is going into it. And this little thing right here, the div F, that's how fast it's expanding. So if you can calculate the little tiny thing and then you can integrate it across a volume, that'll give you the same thing as how much is going into this, into or out of it, of course. So let's calculate div F. Div F is actually pretty easy calculation. Well, in official terms, we kind of represent it like this, a triangle dotted with the force field. And what that really means, the triangle is this thing, d over dx, d over dy, d over dz, and then we're just going to dot that with our force field that we have here. I'm going to dot that with that, which I'll call A, B, and C for now, because I can essentially say that it's going to be like an x partial of that plus the B y partial and then plus the C z partial. So I can just add up the partials. This is the sum of the partials. It's actually really easy to take the divergence, the div, because it's the sum of partials. So let's sum the partials. If we take A, this is B, and this is C, and we take the partial x of A, then we'll be able to find that the div F is just going to be 1, and then the partial y of B is 1, and then the partial z of C is 1. So we get that the div is equal to 3. So now we can use 3 for the div of F, and we can integrate over the volume of a sphere, and that should be pretty easy because we can even pull this thing out and just say 3 times the volume of a sphere. We don't even need to integrate this at all. We could just say 4/3 pi r to the third, because we already know how to integrate a sphere or calculate the volume of a sphere. And then there's the 3 on the outside, so that'll cancel out. You go ahead and that's r of 2. So the answer in the end is just going to be 32 pi.